Hello there. In this video we will be tackling two objectives. We've looked at intersections and distances between different types of objects. So now we're going to look at the distance between a line and a plane. So assuming that the line is parallel to the plane, we've seen a case where we're trying to find an intersection between a line and a plane and we got no solution. So that would be a scenario where there's a distance, a well-defined distance between the line and the plane, and so we'll find that. And then the other case is going to be the distance between two planes. All right. So all of these distances will rely on, or could rely on, the formula where we found the distance between a point on the plane. So if you recall this formula, we have some point x naught, y naught, z naught that's not on the plane, and then we have your plane, a squared plus b squared plus c squared, or I'm sorry, ax plus by plus cz is equal to d. Maybe I should write that down. You got x naught, y naught, z naught, which is a point not on the plane. Let's say point. And then you have the equation of the plane, ax plus by plus cz is equal to d. Okay? And so we have this formula. So that's a neat little formula. And the idea behind that is that if you have a point out here and then you have a plane down here, then you're looking for this vertical distance. Okay, so it turns out that to find the distance between a line and a plane, where the line is parallel to the plane, if we take a look at that line will be parallel to the plane and it'll be passing through an infinite number of points. But we can extract a point on that line and then just find the distance between that point and the plane. Okay, so that's what we're going to do. We're going to take advantage of that formula and use it. So this is the point that's not on the plane. So we got 0, 0, 2. And then the normal vector for the plane is the other thing that we need, a, b, c. And then we also need a d, but d is equal to 1. So the normal vector is 1, 1, 1. And then the d is also equal to 1. All right, so let's use this formula. It's going to be ax, so 1 times x naught is 0, plus b is 1, and let's label this x naught, y naught, and z naught. So x naught is 0, y naught is also 0, so all that disappears. And then the last one is c, so c is also equal to 1, and then this time z naught is equal to 2. And then we have the d, and d is equal to 1. That's not an equals, that's a minus. According to this formula, that's equal to 1. We'll put the absolute value there if needed. I don't think it will be needed. And then the magnitude of the normal vector is 1 plus 1 plus 1, so that's just square root of 3. So in the numerator, we have 2 minus 1, so that's just 1, and then this is root 3. So it looks like the distance between this, in this example, the distance between this line and this plane is going to be 1 over root 3. All right, so that is our first objective for the video. Let's take a look at our second objective for the video. And what I'm going to do is I'm just going to copy this over, because to find the distance between two parallel planes, we can essentially use the same formula, right? But there's something else interesting that can happen, and as nice as this formula is, we can actually come up with a nicer formula. So imagine two parallel planes. So we got two parallel planes that may look something like this. What we can do is we can find a point on the first plane. So let's put a point on the first plane, and that could be your x naught, y naught, z naught. And then you have your second plane over here, which has an equation, and then you can just figure that out. So that is fairly simple. But if we go through this process, let's go through this process. So x naught, y naught, z naught times ABC. So ABC is going to be the normal vector here. ABC. But it also could be the normal vector here, because they're parallel. Then their normal vectors should be the same, or at least collinear, because maybe it might not be exactly the same, but it should be collinear. So maybe your n here might not be exactly equal to a, b, c, but it would certainly be a scalar multiple of a, b, and c. So now let's assume that it's a, b, and c for now, and then so that it's exactly the same. And if it is exactly the same, then this expression over here, let's backtrack a little bit. Let's call this plane P1, P naught, because we're using x naught, y naught, z naught that's on that plane. And let's call this plane P1. So P1 will have ax plus by plus cz equals to d. Now P naught will have an ax plus by plus cz equal to another d. So let's call this d naught. So the dot product of this thing, a, b, c, dotted with x naught, y naught, z naught, is actually something that is very related to the plane. And if you were to put x naught, y naught, z naught, because x naught, y naught, z naught is on this plane, when you put that in there, you should get this whole thing to be equal to d naught. Okay? So that makes our equation even simpler. So maybe I'll copy this again, and here I was talking about how we can come up with a more elegant formula, and let's get ready to show that more elegant formula. And let's just say given two parallel planes, and let's give the plane the names a, x plus, and let's have it have the exact same normal vectors, is equal to, let's call the first one d sub 0, and then the second one will be the same plane. Oops, come on. And I'm just doing some copy and pasting here. D1, then the distance between these two planes is given by, so here I'm going to copy our distance formula and put it here. Oops. So what I was trying to say in this scenario is that this is going to be D1 based on our second graph, but then this dot product of the normal vector and the point on the first plane is actually going to give us D sub 0. So now we have an even simpler formula for the distance between two planes. But one of the key things is that the normal vectors has to be exactly the same. All right, let's take a look at this example where the normal vectors are not the same, but the problem is still claiming that these two planes are parallel. So let's figure out what the normal vectors are for each of these. So the normal vector for this one, let's call this n1, is going to be 5, -3, 1. And the normal vector for this one, n2, is going to be -10, +6, -2. And you can kind of see that there are scalar multiples of each other. In fact, you can write n1 is equal to something with n2. And more specifically, I guess I'll put the scalar over here. It's all the signs can change, and then I would multiply this by 1/2. I guess I could have multiplied n1 by -2 to get the same result. But in any case, this is what we have. All right, so now what we want before we can use this formula, before we can take advantage of this formula, is that we need to have both ends to be exactly the same. So we could do one of two things. We can multiply this equation by -1/2, or we can multiply this first equation by -2, I think. So let's multiply this first equation by -2 times -2. And then this will give me a -10x plus 6y minus 2z is equal to, and importantly, multiply that d, old d, into a new d, and that's going to be -8. Okay, and then now our second plane is going to be -10x plus 6y minus 2z. You can see that they have exactly the same normal now, is equal to -3. That doesn't change. All right, so now to take advantage of our distance formula, our distance will then be equal to, well, the denominator will just be the square root of the normal vector, or the magnitude of the normal vector. So it's 10 squared plus 6 squared plus 2 squared, and I'm eliminating the negative sign because I'm going to square everything anyways. And then now the numerator is just going to be the first d, that's -8, minus the second d, -3. And just for positive sake, we can take the absolute value. So we have -8 plus 3, so I think that's -5, but then with this absolute value, it would be under square root. We have 100, 6 times 6 is 36, 36 plus 4 is 40, so this is a square root of 140, and I don't think that's a perfect square, so we can be done. So that's how you can find the distance between two parallel planes. Like I mentioned, you could have also just found this one point on the plane, and to find a point on the plane, you simply let two of the variables equal to some constants and solve for the third variable. But I think this formula is nice and elegant. The only caveat is that you have to make sure that the normal vectors are identical, because that would change the value of d when you're working it out. All right, I hope that helps. Good luck.